Now we are ready to code the transformer block here. So the transformer block combines multiple modules, for example, the attention module, the multi-head attention module we coded earlier in chapter 3. And then it will also have a bunch of linear layers, where for the linear layers, we also introduced several concepts, for example, layer normalization, Gallo activations, and then also the shortcut connections. So going into this figure here again, what we have done so far in this chapter is we coded the GPT backbone, like the placeholder architecture, and then we were filling in the blanks, the placeholders, for example, layer normalization, Gallo activation, the feedforward module, and then also the shortcut connections in the previous section. Now we have all the building blocks here to code the transformer block, which is a very essential core part of the GPT architecture. So the name transformer block, it's derived from the original transformer architecture proposed in the Attention is All You Need paper. And if we go to the paper, there is this very influential figure that you might have seen before. We actually already talked about this briefly in a previous section. So there's an encoder submodule and a decoder module. And the decoder module is what's used in modern LLMs, in GPT-like LLMs. So the encoder module, you can forget about it for now. It's not used in modern LLMs like GPT. It only focuses on this right subpart here for text generation. And there is this gray block here, and this is the so-called transformer block. So to show it to you in a different figure, maybe that also helps. Here we have the whole GPT model, and there are several aspects to it. We have the tokenized text that goes into the model. For example, every effort moves you as the input text. There are embedding layers, the token and positional embedding layers in the GPT model. And then we already coded the masked multi-head attention module. Now, the masked multi-head attention module is part of this bigger transformer block that combines some other aspects. And here it looks like there's only one transformer block, but as we will see also later, the transformer block is repeated a number of times in this GPT model. So it's actually a very important model or module, and the transformer block takes up most of the LLM. Basically, it's repeated a lot of times, and it's a really important aspect of the LLM. And in this section, we are going to look inside what's contained in this transformer block. So let's go to section 4.5 here. And here we see such a transformer block where it receives embeddings of token embeddings. For example, we have input every effort moves you 4 tokens, and they get encoded into 768 dimensional token embeddings, as we talked about earlier. And these go into this transformer block here. And in the transformer block, we have a layer normalization layer. We have the masked multi-head attention module from the previous chapter. We have dropout optionally. And then here we also, you can see we have the shortcut connections. So this is like one submodule. And then we have another layer norm. We have this feedforward module, where the feedforward module consists of a linear layer, a Gallo activation, and another linear layer. And then optionally, we also have dropout again here. And then this feeds to the next transformer block a number of times. So there are usually in a LLM, there are multiple of these blocks following after each other. But we will get to that in more detail in the next section. Here in this section, we are just concerned with coding this transformer block. So let's get to it and see how we can implement it in code. So for that, let me make a class transformer block, and we are going to use again an n.module from PyTorch. And let me just actually copy and paste some of the code so it's a bit faster, because otherwise the videos are always so long. So here we have the constructor. It again receives our configuration file. Then we have the multi-head attention module from the previous chapter. So I should ideally import it from the previous chapter here. So to make this work, you would have to go in here, make a new file, for example, and call this previous chapters. And in this file, we need to have this multi-head attention code from the previous chapter. Otherwise, it won't work. So let me copy and paste the code inside here. So this is the code from the previous chapter where I have just copy and pasted some of the functions we have defined, the data set from chapter 2, but then also most importantly, the multi-head attention module from chapter 3. Because we have to save this because we are going to import this relative to this notebook. So it's a file previous chapters that contains this multi-head attention class. Okay, so let's work with this now. And let me briefly discuss what we are looking at here. So we have the multi-head attention class, and it is using the configuration file for the input embeddings, embed them, that's 768. The output dimensions, they're also 768 in our case. So this is what we defined up here at the beginning of this chapter. Now, we define a context length, how long our context is allowed to be. Then we define the number of heads, whether we want to use dropout or not, so the dropout rate, and the QKV bias, whether we want to use the bias unit in the linear layers. But this is all things we covered in chapter 3, so I don't want to go into too much detail here. More interestingly, we have now this feedforward module, which we defined in a previous section. And then we also have two places where we have layer norm. So the reason why we instantiate two separate layer norm objects is that they have trainable parameters, and we are using them at two different places. And in both places, we want the network to optimize the parameters. So we won't share the parameters. It won't be like one module that is used in two places. It will be two distinct layer normalization modules. And then, the dropout for another place. So there are multiple places where we use dropout. I think it will become more clear once I implement the forward method. Let's do it like this. And in the forward method, one thing that we need is, of course, the input X. And then let me also copy the code here, so it's a bit faster in the video. So here, what we are looking at is how we are using the things we have defined here in the transformer block. And this will be mimicking what you are seeing here. We have a layer norm, multi-head attention, optionally dropout. We have the shortcut connection here, another layer norm, then the feedforward module, and then optionally dropout again, and then a shortcut connection. So this is the first layer norm here. So first, I should say we are saving this shortcut connection because we are going to add this later. So this is what we are creating here, this first shortcut. Then we have layer norm 1, which you can see here. Then we have the attention, which corresponds to this one. The dropout for this shortcut connection here. So I'm just calling this shortcut connection because it's before it goes in here. You can also give it a different name. It's just, something I came up with, not very creative here. And then we are adding this shortcut connection back. So this is this part corresponds to this first block here that you can see inside the transformer block. Now, next we have another layer norm. So the layer norm, is here. Again, before that, we save the shortcut connection. The shortcut connection you can see here. Right? So then we have a second layer norm, then the feedforward module, which you can see here. This is calling the feedforward module. And then, we have another dropout here. And then we add back the shortcut connection. And this is essentially what you are seeing here. This is the transformer block. And to be honest, there's not much really that goes on inside here. It is essentially just encapsulating multiple of these ideas. And the reason why we even create this transformer block and why we don't add this directly to the LLM is so that we can reuse that. So if I go up again to what we have done in the beginning of this chapter, so you can see we have these embedding layers. Then we have dropout defined here. Maybe ignore that for now. What's interesting is here that we are repeating the transformer block. So there is an argument here or a value we define as n layers. And here we have 12 layers. So that means we are repeating this transformer block 12 times. And then we have a final layer norm and output layer. But so that we can make this code very concise, we encapsulate this in this transformer block class, which you can see here, which we have just coded. So let's just make sure that it works. So I executed this cell, not making the mistake I'm usually making. And then we are trying it out in practice. I'm using a random seed again so that you get the same results that I do. And then let's do a small example. Let's do 2 examples with 4 tokens each. So this would be something similar to here, where we have 1, 2, 3, 4 tokens. And let's just assume they are embedded in a 768 dimensional space, which corresponds to what we have defined here. We will be working with real data soon. So for this part, just to keep it small and self-contained, I'm using this random input, but we will be working with real data soon in chapter 5, so not too far away. And then we define the transformer block. So we do transformer block, and then we provide the configuration file that we had at the top of this notebook. And then, yeah, we can use it. We can do output equals block, and then we have the input here. And that's essentially it. So I can execute this and just take a look at the input shape. So the input shape is 24768, which makes sense. And the output shape should be similar. So here, take a look at the output shape, has the similar size. And why is that important? That's because we have multiple of these transformer blocks, as I mentioned before. And so if we want the next transformer block to be compatible with this transformer block, the input has to be the same size as the output. Otherwise, we will have some complaints in the feedforward network if suddenly the input dimension changes. So yeah, that is all there is for now about the transformer block. And in the next section, we will put everything together into the GPT model architecture.
Get this book at manning.com.